Hi everyone. In this series of videos, we're going to see how we utilize various sugars in our diet and what we do with it, where we put it away, and how we break down our sugar reserves. Of course, we put it away in the form of glycogen, so there's going to be sugar utilization, the big three themes, um, uh, and the reserves of sugars that we put in our bodies, they're all in the form of glycogen, and then when we need it, how we mobilize these reserves. But before we get to that, we need to have some nomenclature taken out of the way. And so this little video is going to be all about sugar notations. So this is a stereo view, I mean, around one carbon, for example, and it's not on one plane, right? So you have these two carbons, the top and bottom uh, being behind the screen, and these groups, the proton and the carbon and the hydroxyl group here, are in front of the screen in real life. However, we project them all on one plane, and that's the Fisher projection, and we see them in a one plane view of the actual carbon. So just to keep in mind that whatever you see drawn like this on a board, in reality, there is more depth to it in space. Okay. So this is the smallest sugar. I mean, it's as we said, they are starting from three minimum carbons, and there's going to be one carbon. Every carbon is going to be bound to oxygen, but only one will be in the keto form, and you see here as an aldehyde, and the other two will be in the hydroxy state. Okay, so as long as you have that, so you have three, between 3 and 7 in real life in our bodies, and number of carbons, and then you have the sugar. And of course, all of them have to have an oxygen, and all but one of the oxygens are in the hydroxy state, and the other one is a keto group. Now, because they differ in space, how they're placed, they always come into two forms, the L and the D form, and we'll see how we can tell them apart. Well, I'll give you a hint now. So you look at the hydroxy group farthest away from the carbonyl, and in this case, if on the Fischer projection, if it's on the right, then you have a D sugar. If it's on the left, you have an L sugar. Why do we need to learn all these things? Because we're going to see enzymes that move the configurations, from D12 and so on and so forth, and more. We've already seen some of them, some epimerases, when we're talking about the sugar interconversions in the Calvin cycle and in the pentose phosphate pathway. So that's glyceraldehyde. Okay, so it's an aldehyde, as you can see here at the very end. But this is our favorite one, so that's glucose. Okay, so it's got 6 carbons, 1 through 6. And you see the various hydroxyl groups on each of these carbons. And of course, the last one, glucose, is an aldose, so it's also an aldehyde. So these 4 carbons, each one of these 4 is a stereo center. Okay, so glyceraldehyde only has one, just this one. Okay, carbon 2. But glucose, for example, has 4 of them. Right? So that opens up all kinds of possibilities, and so that's D-glucose. Why is it D? Okay, again, because the hydroxy group farthest away from the carbonyl is on the right, and that's on the Fischer projection that you see here, and that makes it a D sugar. Now, that's one. So now for every D you have an L, okay, depending on where that guy is. And in total, you have 2 to the 4th, so 16 possible isomers. Okay, so this is the number of possibilities from the exact same number of atoms on this molecule. You get 16 possible isomers. If they only differ at only one center, at only one carbon, then they are called epimers. So that's the definition of an epimer. Okay, all of them are isomers to each other, but if the difference, so now you have a big group, they're all 16 isomers, but for glucose, for example, but if the difference is only at one carbon, at one center, not just one carbon, at one center, then we have those two are called epimers. We explained that already. Why D? Okay, because the hydroxy farthest from the carbonyl is on the right side, and that's the analogy with glyceraldehyde, okay, which only had one center. And these are the different 8. Remember, you have another L version of all of them. These are the different 8 isomers of glucose, depending on how they're arranged, or the hydroxyl groups on its carbon. They're all D. Look at the farthest hydroxyl group. It's always on the right in all of them. Okay, and the blue, the ones that highlighted here in blue, are the ones that are actually found in real life, and we're going to talk about all of them actually: glucose, mannose, and galactose, and how we metabolize them, because they are in our diet. D and L sugars are mirror images of each other, literally. Now, a couple of things that we need to talk about is that in physiological fluids, in cells, more than 95% of the sugar, let's say glucose, is actually found in the closed conformation, where the hydroxy oxygen of the C5 carbon attacks the carbonyl carbon, okay, and then it closes the ring. We've seen this before. And this closed configuration is also found in many conformations, right? And oh, by the way, and if you have this, what we just described happens, let's say, for glucose, these are carbohydrates, and they're called pyranoses. They're carbohydrates with a 6-membered ring, okay? And the ring, it has 5 carbons, 1, 2, 3, 4, 5, and 1 oxygen here. Okay? And you can also have furanoses, which are carbohydrates with a 5-membered ring made of 4 carbons and 1 oxygen. And you got, which already seen, T-ribose, for example. Okay. So these are the closed conformations of the sugars we're going to see. And we're going to pay particular attention to the carbonyl carbon C1, which in the closed configuration is the epimeric carbon, one of the two. And depending on this orientation of the oxygen, if it's up or down relative to the rest of the ring, for example, here it's up, then it has very important consequences in the way sugars are utilized and put away in glycogen and broken down. So there are specific enzymes that really just change the configuration of the epimeric carbon. Those two are called anomers. They only differ in the configuration only at the C1 or sometimes in the C2 carbon. So we have isomers, epimers, which could be anywhere, but the anomers now, we're dealing specifically with this carbon, and sometimes with carbon too. All right. So that's it. All right, so we're going to close at this point, and in the next video, we're going to see how we actually metabolize one by one all these extra sugars.